Okay, so now I want to go through two example problems of two-source interference, just to give you guys an idea about how you have to solve the problems. The second problem will be a little bit more complicated, and we're going to continue practicing that type of problem and learning more about it in next week's video on diffraction. But to get started, let's get a good example of what these types of problems look like. Okay, so often these problems are based on speakers and sound, as I presented in the video before. And a fun music theory fact is that most music is centered around 440 hertz. Okay, that's Verdi's A. So most tuning on guitars and common Western music is based on 440 hertz scales. And that's just because scientifically proven it somehow relaxes humans' minds. It's easier to listen to. So at a concert, an audience member is seated away from two speakers as shown below. Use your knowledge of interference to predict whether the person, this guy, is going to have an enhanced experience with 440 hertz or not. So what does enhanced experience mean? So if he's sitting here, is the path length here and the path length there going to be such that the crest of a wave here is going to overlap with the crest of the wave there to make double the amplitude and a strong intensity of 440 hertz? Or is there going to be sound cancellation? And that's what we're looking for. So the key to solving this problem is try to look at these two different path lengths, okay? And if, let's just call this B and let's call that A. So if I see that path length B minus path length A is equal to a whole wavelength, then it's constructive. Do you guys remember that? Okay, and on the other hand, if it's equal to 1/2 of a wavelength, it's destructive. So the enhanced experience is going to be the constructive path. The horrible experience, bad seating, want my money back, is if that wavelength is going to be, that path length difference is going to be on the order of 1/2 a wavelength. So how do we go about solving that? Okay, how would you look at this problem before I help you out to try to figure out the path length difference? You have 20 meters being that dimension, 4 meters being that dimension, and you have that being the length between the second speaker and the person sitting there. And the sound being produced by these speakers is 440 hertz. So this is the logic. I need to find my path length difference, and I also need to know my wavelength of that sound. That's frequency, that's not wavelength. So I'll have to play around with that. Okay, so let's get to it. All right, so what I can do right now, first I'm gonna start figuring out a few things. I'd like to figure out, instead of frequency, I want to have the wavelength. Okay, so to solve for the wavelength of 440 hertz, I use the wave equation. So I'm just going to say this is my first step to the problem. The wave equation is equal to lambda times frequency. So the speed of sound divided by the frequency is going to be my wavelength. Okay, so 340 meters per second, which is the speed of sound typically, is going to be divided by 440 hertz, which is going to give me a wavelength of around 0.77 meters. Okay, so now I know what my wavelength is. After figuring out my wavelength, I'm gonna move this all over here. So after finding out my wavelength, I can then try to calculate the path length. Okay, so I have the path length A, which is 20 meters, and I need to solve for path length B, and I see that this is a right-handed triangle. Okay, so I'm just going to use Pythagoras' theorem of a squared plus b squared is equal to c squared to find that length, which is I'm going to call label C, the hypotenuse. So 20 meters squared plus 4 meters squared is equal to c squared. If I square root 20 meters squared plus 4 meters squared, that's going to be c. And in this case, the square root of 416, the square root of 416 is going to be equal to around 20 I got it written down here, I'm cheating, 20.39 meters. Okay, so that's going to be path length B. So now to find the path length difference, so path length difference is equal to 20.39 meters minus 20 meters, which is equal to 0.39 meters. Now, is 0.39 meters a full wavelength, or a partial wavelength. The full wavelength we calculated as being 0.77 meters. 0.39 meters is approximately half of that. Okay, so really the path length difference here is going to be a half wavelength. Which is around like a half. So if that's a half wavelength, is it going to be good quality sound or bad quality? So a crest is going to be overlapping with a trough. It's going to cancel. So if you had seats, now that's the interesting thing. You're sitting right in front of the speaker, you'd be thinking that you're going to get a good quality sound. But in fact, in this setup, even sitting right in front of the speaker is going to give you a poor quality sound. And this actually happens in concerts. So somebody who's testing the sound, if he's standing over here, would ask the engineer to up the volume, make the volume louder and louder and louder, and eventually he'll start to hear something. But the people that are sitting in perfectly acoustic places, like right in between, are going to get completely deaf, okay? Because the sound here is always canceling, all right? So that's just a good example problem of something that would be illogical. Standing in front of a speaker gives me horrible quality sound. That's pretty interesting. Okay, the next problem is a little bit more complicated, okay? And I'm going to introduce you to a formula that we're going to derive in the next week, but it's important to be able to calculate these things. So I have the same speaker setup. These two speakers are 440 hertz, and they're 4 meters apart. And now this person is standing right in between. So this person here is getting really good quality sound because the path length of A and B are exactly the same. There's no difference. So a crest is going to overlap with a crest, and this person is going to have double the amplitude and a pretty strong intensity. But the question's asking, how far does he have to walk? As soon as he starts walking away, remember, if he walks right in front of the speaker, it's horrible quality sound. So how far does this person have to walk until all of a sudden the sound quality becomes good again? As soon as this person leaves that point, the sound quality is going to go down. And then when he gets to this point, the path length difference is going to be perfect. Okay, so if I look at that, and then I look at, let's get a better color. If I look at that, and then I look at that, okay, here I got the path length of that, and then the path length of that. If I subtract the length of B minus A, that should be a full wavelength, 0.77 meters, okay? So what we're going to do is we're going to try to figure out how we can calculate that. Now you can do this with geometry. It's a little complicated geometry, but you'd be able to figure this out. And we're going to learn the formula to be able to do this, and the formula comes from geometry. And I'm going to give you that derivation next week, okay, which you're going to have to memorize. But this comes from Young's double slit formula, okay? So I'll be able to calculate the total distance that he has to travel such that the path length difference is going to be one full wavelength, okay? And that formula looks like this, okay? So that distance x that I would have to walk is going to be equal to I'm going to give you some letters here, and I'm going to define what those letters are. D, which is the distance that that person is away from that parallel line from the speaker. This would be 20 meters. Okay, and then the next thing here would be the wavelength of the source divided by little d, which is the separation of these two speakers. So little d is the separation of these two speakers. Capital D is the distance that that person is away from the speakers, and lambda is the wavelength. So in order to solve that to solve how far that person is going to have to walk, I just have to plug in these numbers. So D is 20 meters. Lambda we said was 0.77 meters. And little d is going to be 4 meters. Okay? So in this case, x is going to be equal to, I have it over here, x is equal to 3.86 meters. If I put that through a calculator, what that solution would say is that I would have to walk a total of 3.86 meters before that sound quality becomes good again. Okay? And then if I work out this geometry, so 3.86 meters, okay, so if I walk 3.86 meters up this way, okay, and I'm 20 meters away, and then I work out some geometry with Pythagoras' theorem, I would find that the path length difference between this and this is going to be one full wavelength, only at that point. Okay, and this formula, which you have in your data booklet, allows you to calculate that. So this is really important. Now, the data booklet might use an X or it might use an S in this point here. And so it's important that you check that out for yourself. Okay, it depends on how you define the variables. Okay, and I have a drawing down here that kind of demonstrates what happens. I worked out the geometry by myself later on, and I'll explain how I did that. Okay, I just made some parallel lines over here. If my distance that I calculated there was 3.86 meters, that means that this here is 2 meters. Okay, so that's 2 meters over here. And that person would have to walk an extra 1.86 meters beyond the speaker. Okay, this is 20 meters. Okay, so if I did Pythagoras' theorem, I'd be able to solve for 20.07 meters being the path length of A. Okay, and then to solve for the path length of B, okay, I'm just going to extend this line down here. This is 20 meters, and this would be 5.86 meters. Sorry, it'd be 5.86 meters in total from there down to here. And so then using Pythagoras' theorem, I was able to solve for that path length of B is 20.84 meters. Okay, so if you subtract 20.84 meters from 20.07, that'll give me one full wavelength, 0.77 meters. Okay, so that's just a proof that this geometry thing works. Okay, so this equation that you have in your data booklet is used for 2-point interference. Okay, where it tells you how far somebody would have to walk from the center there to be able to hear another loud sound. Okay, that's that.